This lab will look more into conservation of mechanical energy about the springs. Please go through the introduction and then read through the whole lab progress, then we'll get it started into the lab. First, we need to do some data collecting. First, I'm going to use the balance and then put the object on the balance and record the data. 50.75 gram. And this is the spring we're going to be using. It is labeled as 15 Newton per meter. Place the spring that I will be using on the meter stick. It is easier to tell the relaxed length. It is about 4.75 centimeters. Next, I'm going to place the object on the hook so that way it will stretch the length of the spring. Wait until it stops moving, then I'll record the length. Place your meter stick right by the side and wait until it stops moving. I don't know if you can tell clear from the screen, I recorded as 6.5 centimeters. So I'm going to repeat that progress 3 more times, so that way I have 4 different trials. I'll fill in the data table and share with you after. From this, a little bit calculation, analyze part 1, it does tell you how to do the calculation. So please pay attention and be aware with that, and then read it through, followed by the step. For the percent of error, just be aware that the spring that we're using was labeled as 15 Newton per meter, so you will use that as your theoretical value, and the experimental value will be the average you find for the spring constant. So for part 2, starting part 2, I need to find out the distance above the table, so I use the empty stands and make sure it have no weight on it, almost no mass on it, and then that way it's not stretching the spring. Make sure the spring wasn't stretched, and then I find out the height above the table is 34.8 centimeters. Place the object on a balance, and then it shows the first trial is 60.82 grams. Now place the motion sensor right below the spring, and then place the object on the spring and make sure it is not stretching the spring yet, and click collect on your device and gently let it drop. So here's the 2 different graphs. On the top it's position versus time graph, on the bottom is velocity versus time graph. For this point right now, we will be more focusing on the position versus time graph. There's 2 tables we need to fill out. One is the highest point and the lowest point. So first trial, mass is 60.82 gram, and then let's see where's the highest point. As you can see from the data point, it tells you 0.62 seconds. The highest point was about 0.337 meters above the table. So that's your highest point, and also that was a height in meters above the table. Then you can use that as also, if you use 0.337, which is the height above the table, subtract the initial height above the table, that should give you the elongation, which can help you to find out what is a potential energy elastic. Now let's move on to the lowest point. About 0.80 seconds, the object is about 0.297 meters above the table. And as you can see from the graph, this is the lowest point. So write down 0.297, and this is also the height above the table. Using a similar concept, you should be able to find out what is the elongation by subtracting this number from the initial height then you should be able to find out potential energy elastic. Potential energy gravity, which is mass times height times gravity, which is 9.81. Then mechanical energy total is what potential energy gravity plus potential energy elastic right here. I'll fill out the data table and share with you after, so you should be able to finish all the calculation.